You can mute your mic, Namyung. So do you all remember what we have done till now? Till now we have studied a particular property. We were studying the particular property of what? Of any matter or material. So what was that called? It was called elasticity. Now this is just a property of any material. And after that, what did we do? We have a body, let's say. And if we apply certain amount of pressure or certain amount of force, what will happen? Either there will be no change or the body gets deformed. It gets elongated in this direction. But always there will be certain restoring force which will always try to bring it back to its original state. This one is called your restoring force. And if there is a deformation or let's say change in dimension. What I mean by change in dimension is either there is a change in length, breadth or height or either three or all of the three. Now the deformation may occur depending on what a different kind of what materials, which will depend on what? Your modulus, which was called, how do we define the modulus? As stress by strain. Stress was basically pressure or restoring pressure or restoring force per unit area. And strain was what? Change in your dimension to your original dimension. So today we are going to do what? First we are going to start with your one of the moduli. First one is your Young's modulus. So what is a Young's modulus? It is basically the constant which is sitting in front of that stress by strain. Now, basically, Young's modulus deals with what? If there is a deformation in one dimension. Now, if you consider a very long wire. If you consider a very long wire, let's consider this as a very long wire. Are you being able to see this? Or should I make it slightly larger?
It's okay, sir.
It's fine, no? Now if we apply certain amount of force over here, then what will happen? It will get deformed and it will get elongated in this direction. Let's call this as delta L and let's call the original length to be L. Clear? Now, this is for roughly for a one-dimensional object. For one-dimensional object, you have that name of that constant is called your Young's modulus. Now Young's modulus is given by E, which is basically what? Stress was force per unit area. What was strain? Was change in length to its original length. Clear? Should I write it delta L or L? Let's write it L so it will be easier for you all to see. A into L. Basically, L is change in length. Clear? Is it clear?
Yes, sir.
Now you all see what does the Young's modulus means. If your Young's modulus is larger, what does that mean? Does that mean what? Does that mean more amount of force will be required to stretch it?
Yes, sir.
Basically, because you can directly say it's directly proportional to your force applied. Let's consider this L as what? Your constant, and area of cross section is also constant roughly. Let's say the area of cross section does not change much. So you can see there are only two variables. One is your force, one is your length. Clear? Now, if you consider force as constant, then what? Your Young's modulus depends on is inversely proportional to your length. Clear? So larger the Young's modulus, what?
Larger the force required.
Larger the force required, okay. E large means F should be large. Let's make some deduction from here. Now E large means L should be less. Can you see?
Yes, sir.
If your Young's modulus is large, that means your change in dimension will be less. Now, if your Young's modulus is large, the amount of force required to change in dimension is more. So can you give me one example of such material? Let's compare it between two materials having less and larger Young's modulus. What about steel and rubber? Any gases which will have larger Young's modulus? Which will have larger Young's modulus? Any guesses? If you apply the same amount of force, what will happen? Which one will stretch more, steel or rubber?
Rubber.
Rubber. Okay, which means here for F at F constant, let's write this L change in length of steel, this of rubber. We can say the of rubber is larger. The change in dimension of rubber is larger as compared to steel. Which means what? We can make a deduction from here. What we can say? The Young's modulus of which one will be larger? Because this is inversely proportional. So Young's modulus of steel is larger than Young's modulus of rubber. Is this point clear?
Yes, sir.
I believe it's clear. Now let's go to your two-dimensional object. Now if we consider and if we do the same concept and move to your two-dimensional, how the plane will change. Basically your two-dimensional object is what? Is just a plane. Now can you give me an example of how the plane will change? This is basically given by, can you see this figure over here?
Yes, sir.
Is given by shearing modulus. Basically it deals with what? Your two-dimensional deformation or two-dimensional change. Now can you see originally let's say it was a square, and after applying force tangentially, the force applied should be what?
Tangential.
Applied should be tangential to the plane. Do you know what does applying force tangentially means?
Applying the force on the surface.
On the surface. In a circle, let's consider this as a circle. Where will be the tangential force will be? How do we make a tangential force?
Right on the surface, sir.
It will be something like this. Okay. Always perpendicular with the radius. That is your tangential force. I think you have done the same thing in your central force problem or something. In uniform circular motion, I think you all have done. Now the tangential force always acts on a plane. Can you see over here? If we zoom this over a large plane, then roughly this curvature will be very small. So it can be like a straight line, this small portion which is sitting over here. Now the tangential force is always like this, always towards the plane. Now if we apply a tangential force over there, then what will happen? A deformation will occur. Just like your book. You have this book which is sitting over here. Something like this, a book which will be sitting over here like this. Now if you apply force over here, what will happen? Then this will become something like this. I think everyone has noticed this. Not exactly like this, but somewhat like this. Have you all noticed this?
Yes, sir.
Now, can you see there is a deformation by an angle?
Yes, sir.
There is a deformation, but at an angle. Basically, there is a deformation in plane. So how much the deformation is basically theta or phi. Let's put it theta, okay? This is a change in angle. Now, if you apply a tangential force, now the plane has slightly moved. So that's why there is what? There is what? There is what? There is a deformation by an angle phi. Now, what will happen if you apply a same amount of force on both the side? What will happen? What will happen? Any guesses? If you apply tangential force on top and also at the bottom, what will happen?
It won't get deformed.
No, it won't get deformed. The whole body will move. Okay, so the most important point is that the tangential force should be applied only on one side of the plane. Clear? So the amount of deformation, which is delta x, do you know why we are being able to take this delta x as theta? First, let me write the formula. Then you will be able to see. Basically, the shearing modulus or the rigidity modulus. And this strain is called here what? Shearing strain. S-H-E-A-R-I-N-G. Shearing strain. Shearing strain usually occur in what? Here, two-dimensional, when the force is applied on a plane. Rigidity, the modulus is given by rigidity modulus, which is again the definition is same, stress by strain, but the definition now changes to tangential stress by shearing strain. Clear? Now your tangential stress is again the same thing, which is again force per unit area, and shearing strain is basically what? Yeah, phi or theta. We were using theta, sorry, basically theta. Now, do you know why we are being able to write this as theta? Let's consider this, and there is a deformation in this manner. Actually, the deformation is extremely small for a time being. I'm just writing it to be large. And basically, this should be a deformation. Can you see? This should be actually a change in the dimension. Originally, it was over here. Now it has moved over here. But we are being able to write in terms of theta. Do you know why? What is sine theta? What is sine theta? Basically, hypotenuse is this one, which is roughly we can take the hypotenuse to be of same size. Let's consider this as 1. Clear? Let's put this as 1. This is also roughly 1. Let's say the deformation is extremely small, so we can roughly take this as 1. Now, when the angle theta is extremely small or delta x is extremely small, then we can approximate theta to be delta x. So that's why we are being able to put what? Delta x as theta. Shearing. Actually, this is length 1. Strain should be what? Strain should be what? Change in dimension by original dimension. Let's put it x. The original dimension or the length was usually what? 1. Now deformation is delta x. For x, I'm taking 1, okay? Or should I take it L? Either way, it's fine. If we take this as L, then there is a deformation of delta x. Then we define this as delta x by L, which is basically what? Sine theta. Hypotenuse, let's consider this. This is also of length L. This is also of length L. Then roughly this can be taken as what? L if the angle is extremely small. So that's why what will happen when delta x is extremely small, we can approximate sine theta as just theta, delta x by L. So basically this we can put it in terms of your shearing strain. Or the easiest method is just the change in angle. Is this point clear? Okay. Now we move to a point when we have a deformation in your 3 dimension or 3D. Basically, this is what your bulk modulus. Bulk modulus. Now again, what kind of expansion should there be for the bulk modulus to occur? The deformation should
It
be.
will expand by volume.
Have you ever blown the balloon? Balloon? I think everyone has blown the balloon. Usually this will be of this size. Then you, when you start blowing or applying pressure over here, what? It will get expanded. Yeah, let's consider this as a sphere. Perfect sphere. Let's consider the balloon as a perfect sphere. Initially it was this side. After blowing this, what? It will increase in size. Now this is basically what? Your bulk modulus. Can you see the volume has increased? Initially the balloon was of this size. Now it has
Yes, sir.
increased or expanded because the force was applied on all the side by putting what? By blowing or applying pressure. Is this point clear?
Yes, sir.
Now let's do it in a cube. Or I think in the balloon itself, I think it will be easier. So basically what will be your bulk modulus will be given by K. Basically it is what? Bulk stress by bulk strain. Clear? Bulk stress is what? Force per unit area again. Bulk strain is what? Change in volume. Basically the change in volume, can you see? Change in volume. Change in volume over here is V and actual volume was V. Clear? So here bulk modulus will be given by what? F A V by V. Now let's consider one example to be. Let's say your balloon initially was of what radius? Initially a balloon was of this size. Of this size. What should be the, let's consider one radius. Let's consider the radius of this balloon to be what? You can pick any number.
X.
1 meter. Centimeter. How much?
2 meter.
5 meter. 2 meter. How much?
2 meter.
Okay, let's put it as 2 meter. Initially, a balloon was of size of 2 meter. Now you started blowing or you applied a certain amount of force. Clear? The pressure of force which you applied was how much force? 50 Newton, 100 Newton, 100 Newton, and the pressure which it produced was, let's say, force per unit area. 100 plus pi r square, basically, or 4 pi r square, no? Is this point clear why pressure is force per unit area? Leave it. You are applying 100 Newton of pressure. By applying 100 Newton of pressure, what happened? It expanded to this size. Now the radius has changed to what? 4 meter, 3 meter. Let's consider 3 meter. Now, can you tell me what is the change in volume? Now to compute or Now to compute your bulk modulus, what the things we need? Force, we already have. Amount of force applied is 100 Newton. And force per unit area, how much force is applied per unit area is what? What will be the area of this sphere? Area of sphere is what? Area of sphere is 4 pi r square. So the area will be how much? 4 pi 2 square. 16 pi. So your pressure will be, or force is 100 Newton, area is 16 pi, and your volume is, what is your volume? Volume is 4 by 3 pi r cube, which is basically 4 by 3 pi into r is how much? 2 to the power 3. 8 4 8s are 32. 32 pi by 3. Basically, you again got the volume to be 32 pi by 3. But the only thing is what? Your small volume V is getting left out. This volume we have to evaluate. Now, how to evaluate the small change in volume? The easiest method is now get the volume of this minus the volume of this. I think we can always do that. Is larger volume minus smaller volume. Now the larger volume is given by what? 4 by 3 pi. What is the radius? 3 cube minus this we have already evaluated. How much that is? 32 pi by 3. Now after evaluation of this, how much you will get? 4 9s are 36. 36 pi minus 32 pi by 3. Now this is basically your change in your dimension. Is it clear?
Yes, sir.
Yes, sir.
Now finally you will be able to evaluate what? From here we can take 2 also common. Let's take 2 common. 2 pi as common. Then how much you will get? 2 1s are 2, 2 8s are 16. I think we can take a lot common. 4. That we can take 4 also common. 4 pi less because it has been multiplied by 4. So it will be how much? 4 9s are minus 8 into by 3 pi. So how much you will get? 4 pi 27 minus 8 by 3, which is basically how much? 19. 19 by 3. Now you plug this over there in your bulk modulus. So finally you will end up with bulk modulus to be what? 100 by 16 pi into 32 pi by 3 into 4 pi into 19 into 3. Is this point clear? This will go 2 times. This can cancel out. So K will be how much? 200 by 4 pi into 19. This will also go 50 times. 50 by 19 pi. So this is your Young's modulus. Is it clear now? How you?
Yes, sir.
Yes, this is not your Young's modulus. This is basically your bulk modulus. This is how you evaluate a bulk modulus. Now same thing goes for your what? For what? Your Young's modulus and for your rigidity modulus. Now we will talk about one small thing today about your Poisson's ratio. Because one thing previously we didn't take into account is what? If you have a cylinder which is slightly larger. Clear? Now if you apply certain amount of force, what will happen? what will happen? It will get elongated, that is for sure. Yes or no?
Yes, sir.
But
Yes,
at the
sir.
same time, will it get shrinked over here? Will it shrink over here? The length will increase, but the area of cross section will decrease. Basically, it will look something like this. It will get elongated over here, but it gets squeezed over there. It will be something like this because the volume has to be maintained roughly. Actually, the volume has to be maintained, so that's why it will get elongated something in this manner. Is this point clear?
Yes, sir.
Yes,
Because
sir.
when you get or when you
Yes, sir.
where you put a certain amount of force, what it will get elongated, but what its size will decrease. You can see there is a decrease in size. Initially, it has a radius of what? R. Now it became R1. Now basically the change in radius is what? Delta R. Now over here, initially it was of length L. Now it has been elongated by an amount of what? Delta L. Can you see now there is a strain or deformation in both the side? Now there are two kind of strain. Now this two kind of strain are defined as what? Your lateral strain and longitudinal strain. Now can you tell me which is lateral, which is longitudinal? Lateral is basically the change in this radius, and longitudinal is basically a change in your length. Is this point clear? So this can be defined as delta R by actual radius. This can be defined as delta L by actual length. So whenever we apply certain amount of force, there will be what? Two kind of deformation, which is it will deform laterally and otherwise it can deform longitudinally. So depending on that, we have what? Your two kind of strain. These are lateral strain and longitudinal strain. Now the force applied over here was F in this direction. Now there is certain thing which is called here Poisson's ratio. Poisson's ratio. Poisson Poisson's ratio. It is defined as a ratio of what? Defined as a ratio of lateral strain by longitudinal strain. Basically, your Poisson's ratio is given by nu. So this is how you write nu, okay? It's similar to V. I think you have seen this in frequency also usually we use. It is given by nu, which is your lateral strain by longitudinal strain. So lateral strain is basically what? Delta R by R, and longitudinal strain is what? Delta L by L. Now basically this is your Poisson's ratio. This ratio is called. Do you have any problem or do you have any questions till now? Now you can ask. So we are going to stop over here. So tomorrow we are going to find a relation between different moduli. Basically, what did we do? To summarize, what did we do today? We consider three kind of modulus. If we apply certain amount of force in different system or different kind of in different dimension, what will happen is for one dimension we have there's a deformation in length, so it is called when we apply force it will branch into in what dimension we are applying. One dimension is called here Young's modulus. Young's modulus, which is given by E. And on two dimension, we have what? Shearing stress, which will give you rigidity modulus, DT modulus, which was given by what? G. And in your three dimension, what we have here? Bulk modulus. Modulus, which is given by your K. What did we use? K, no? So these are the three quantities. On different dimension, what? For your rigidity modulus, the force was what? Your shearing stress was there. And for the bulk modulus, there is a continuous expansion or contraction of the whole body. For a Young's modulus, it was just change in length. Now, another thing we start was Poisson's ratio, which is given by nu, which was basically what? Your change in this or transverse or basically a lateral strain by lateral stress. Because when we apply a force, there is a deformation both in your radius and also in, basically there is change in dimension of your surface area and on length. And depending on that, we called it as, it was a ratio of lateral stress by longitudinal strain. So what will be the dimension of Poisson's ratio? No dimension. Because strain does not have any dimension. And also you are dividing strain by strain. So do you have any questions? So we are going to stop over here. If you want to ask any question, now you can ask. Are all the points completely clear?
Yes, sir.
Any questions?
No, sir.
No, sir.
Okay.
No, sir.
Then fine, we'll stop over here. Now, who